Welcome back to Unit 2.2, and in this video we are going to be looking at rusting and methods for preventing rust. So we're going to start on page 17 of your booklet, and we're going to have a look first of all at what rusting is. So you'll be very familiar with rust. It's something you probably see most days around you. It could be on your trampoline at home, it could be on school gates, it could be on your car, it could be on the hinges of a garden gate or something like that. It's something you see all around you, and it's something that can be very problematic. But you may never have thought about it before that rusting is actually a chemical reaction. So rusting is a chemical reaction. It's a type of corrosion that happens when iron comes in contact with water and oxygen. Those things are really, really important. It's really important because rusting only refers to iron. So other metals will corrode, but rusting is a special type of corrosion that refers only to iron or perhaps alloys that contain iron. So if you have, for example, nickel that corrodes, you cannot say that it rusts. So you can't say nickel rusts or copper rusts or whatever. You can only use the word rust when you're referring to iron or alloys that contain iron. During rusting, iron is actually oxidized to iron oxide, and iron oxide is a simplified name for rust. So we know from our previous video on this topic that oxidation is the gain of oxygen. So iron is gaining oxygen, and the gain of oxygen, as you know, is defined as oxidation. So you could add that to your notes. Quite often the iron oxide will then fall off. It's a more kind of brittle substance that will then fall off, and that exposes more iron, and when that gets in contact with the air and water, it will also rust, and you can see iron structures starting to wear away because you're forming this iron oxide which then falls away, and then the iron underneath it will react, form more iron oxide and fall away, and so on. The next few points are really important, and actually you can get a couple of really easy marks in your exam for this. So the first thing is the chemical name for rust. The chemical name for rust is hydrated iron oxide. So think about that name. It has got three components to it. Hydrated iron oxide. Where do those three components come from? Well, in order for rusting to occur, we need water, we also need iron, and we also need oxygen. So you can see I've done it in three different colours there. And those three things that we need for rust actually appear in the name. So hydrated refers to the water, iron obviously refers to the iron, and oxide refers to the oxygen that we need. So when these three things react together, we get hydrated iron oxide, which is rust. Now you'll see that our iron has a valency or an oxidation number in brackets there. You must include that in the name as well. So it's the 3+ version of iron in this compound. So it's iron 3 oxide. But again, think about it as there's three things that we need for rust. There's three parts of the name. And so this is iron 3. That's maybe a way that you can remember this. So it's hydrated iron 3 oxide. That would give you 2 marks in an exam, so it's really important that you learn that name and you learn it in full. Then you must also learn the chemical formula for rust. So let's take the iron 3 oxide part first. So let's have a think about it. We can see here that iron has a valency of 3 from that number 3 in the brackets. Then oxide is just oxygen. And if you look in your periodic table, oxygen is in group 6, so it has a valency of 2. We can't simplify that down at all, so we just simply swap and drop, and that gets us Fe2O3. So that's the start of our name, but it is hydrated as well, so we must show that there are water molecules bonded to this iron oxide as well. How we show that, you might remember it with our test for water with copper sulfate. We use anhydrous copper sulfate, and then it forms hydrated copper sulfate. And how we show that there's waters attached is we do a big dot that shows that water is bonded, And then we're going to put the letter X in, just like you do in maths if you were solving for an unknown number. X is a certain number. And then simply our formula for water, H2O. So it's Fe2O3 dot XH2O. So that X just means a number. There might be 2 water molecules bonded, there might be 3 water molecules bonded, there could be 10 water molecules bonded. So that X is just showing us that there are a certain number of water molecules bonded. It doesn't have to be a certain number to make it rust, it's just however many water molecules. And finally, if you were asked for a word equation for rusting, you simply have to think of the 3 things that are needed for rusting, the 3 things that react together, and they go in the left-hand side of your equation. So we have iron reacting with water and oxygen, so it's iron plus water plus oxygen, and that reacts to give hydrated iron 3 oxide. And don't forget about that little 3 in the brackets. And then just another reminder that only iron and steel rust. Only iron and steel rust. Other metals corrode, so you should never refer to, for example, if you were saying that copper doesn't react with water, you would never say copper doesn't rust, because copper would never rust because it's not iron. So you would say copper doesn't corrode or copper doesn't react with water. So you can only use the term rust when you're referring to iron and steel. Why can you refer to it when you're referring to steel? That's because steel is an alloy of iron and carbon. In other words, it's a mixture of iron and carbon, and so the iron within the mixture will rust. If it's exposed to water and oxygen, it will react with those to give hydrated iron 3 oxide, which we know is rust. So only use the word rusting when we're referring to iron and steel. So top half of that page, really important that you know the name for rust as hydrated iron 3 oxide. You know the chemical formula as Fe2O3.XH2O, that you could write the word equation for rusting if you were asked, and that you know that 3 things are needed for rusting: water, iron and oxygen. We're going to look now at a rusting investigation to essentially prove that you need water and oxygen for rusting to occur, or whether if you just had oxygen present would rusting occur, or if you just had water present would rusting occur. This can come up from time to time on exams, so it's important that you know this experiment, that you can recognise the different components that are added. We're going to look over on the next page at 4 different conditions, and we'll place an iron nail in those 4 different conditions. We'll predict whether rusting will occur, and then see if we're right. A few things to note. First of all, cold water contains dissolved oxygen. That's why fish can survive in water. It's not because they breathe water, it's because they can take the oxygen out of the water using their gills, and they can do respiration that way. So if there was no oxygen in water, then actually life couldn't survive in water, plants or marine life as well. Boiled water, however, contains less dissolved oxygen. Essentially, the solubility of a gas decreases with temperature. So the higher the temperature is, the lower the solubility of the gas. So that's why if you put, say for example, a can of Coke in the fridge and it's really cold, it will feel even more fizzy when you drink it than if you'd left it sitting out at room temperature, or even in a hot day, it'll feel quite flat. And that's because the colder the Coke is, the more carbon dioxide bubbles can be dissolved in it, and that's what makes it fizzy. So the higher the temperature of water, the less gas can dissolve in it. And that's why actually if lakes or rivers get too warm, then fish can start to die in them, because there's less dissolved oxygen in it. So we're going to see a condition for rusting here that contains boiled water, and that's essentially to remove the oxygen. Now it's very hard to remove all of the oxygen, but that's the aim of that one, to boil the water and remove all the oxygen. And then there's going to be a thin layer of oil on top, and that will prevent oxygen from redissolving when the water cools down. So with the boiled water one, we're removing the oxygen and then putting a layer of oil on top to stop any oxygen then dissolving back in. Normal air contains oxygen and water vapour, so we know that on a cold winter morning, sometimes when you open your blinds or open your curtains in the morning, you'll see that there's condensation on your window, and that's because water vapour from the air, so in other words water in the gas form, essentially steam, when it meets the cold surface of your window, it will condense and cool down and form a liquid. So you'll see almost like a liquid on your window. Same thing, go back to that can of Coke. When you take a really cold can of Coke out of the fridge, you'll see those water droplets on the outside of the surface. It's not that the water is seeping out of the can, it's because the water vapour in the air is meeting that cold surface of the can of Coke, and it is then condensing from a gas to a liquid on your cold can of Coke. Water contains dissolved oxygen, and we've already said that above. And then the last thing, anhydrous calcium chloride, is what we call a drying agent. Essentially what it does is remove any moisture from the air. So if we put anhydrous calcium chloride in a test tube, it will remove the moisture from that from the air in that test tube. That's what is sometimes used in those little packets that you get if you buy a new bag or if you buy a new pair of shoes. There'll be that little packet. It can sometimes contain anhydrous calcium chloride. Essentially it's there to remove any moisture from inside the box or whatever it may be. So over on the next page, page 18 in your notes, you can see a diagram of the rusting investigation that we're going to look at here. You can see that there are 4 different environments of our iron nail. So the nail in our each of our test tube is an iron nail. If you want, you can add that to your diagram. So you can see 4 different environments, and essentially this is providing 4 different conditions of our iron nail. So we've got test tube A, in which we have air. Now remember from the previous page, we talked about how air contains oxygen and it also contains water vapour as well. In test tube B, we have our iron nail in air again, but we have a drying agent, this time calcium chloride. Have a think about what the drying agent does. It removes the water. Then we've got test tube C. Test tube C has an iron nail sitting in some cold water. Now that may not have photocopied very well the layer of water, so you might want to just put a line across there to show that that iron nail is in water. Remember, we discussed in the previous page that water contains dissolved oxygen in it. Again, that's how fish and marine life can exist in water. And then test tube D, we've got some boiled water. What is the point of boiling the water again? We boil the water to remove the oxygen. Remember, the higher the temperature of water, the less oxygen can dissolve in it. So the water is boiled to remove the oxygen, and then we put the layer of oil on top to prevent oxygen from dissolving back in when the water cools down. So having a think about those 4 different conditions, what I'd like you to do now is to pause the video and write a prediction of what you think will happen. Essentially what I want you to think about is in which test tubes will you see rusting occur. But I don't want you to just simply write that. For example, if you think A and B are going to rust, don't just write A and B are going to rust. That's it. What I want you to do is really think through which test tubes are you going to see rusting occurring in and why. And for those test tubes that you think there'll be no rusting, write down why rusting won't occur. So you're making a prediction at this point. If it's wrong, that doesn't matter at this stage. We're going to look at the results of this experiment and then we will have a chat about why rusting occurs in some of these test tubes but not others. So pause the video now, write a prediction as detailed as you can for this. So essentially you're answering these questions. In which test tubes will you see rusting and why? And in which test tubes will no rusting occur and why not? So pause the video now and answer those questions to write your prediction. So now that you've made a prediction, let's have a look at the results. So here I've got a test tube A, B, C, D set up. I've set this up at home. I've left them, the iron nails, in their different environments. for about a week or just over a week. Because as you know, rusting isn't something that happens really quickly. It's quite a slow reaction, so we have to leave it over time. So let's have a look a little bit closer at each of the nails and see what's happened in each. So hopefully you can see from this image very clearly that rusting has occurred in test tube A. Rusting has not occurred in test tube B. Rusting has occurred in test tube C. And rusting has not occurred in test tube D. Let's have a closer look at each. So A, first of all, you can see that rusting has occurred on the iron nail. Maybe not as much as test tube C, but it has occurred. Why is that? Well, this iron nail is in air, and remember that air contains oxygen and it also contains water vapour. So oxygen is present, water is present, and so rusting has occurred on this iron nail. Test tube B then, test tube B was in an environment of anhydrous calcium chloride. You can see the little white pellets there. That is a drying agent that is there to remove the water vapour from that environment. It removes any water that is present. So therefore there's no water, and rusting has not occurred in test tube B. In test tube C, you can see that significant rusting has occurred. You can see that brown hydrated iron oxide, which is rust, and you can see that some of it has already started to flake off and sit at the bottom, and that means that fresh iron is being exposed to the water and oxygen, and so even more rusting occurs, more hydrated iron oxide is produced. And then finally in test tube D, we had our boiled water, and you can see your layer of oil there at the top as well. And you can see that rusting has not occurred in this test tube. And remember, that is because boiling the water removed the oxygen. So essentially we just have water here with no oxygen. And so rusting has not occurred. So let's have a look at the results table on page 18 and see if we can fill this in. So with test tube A, first of all, the environment was just simply air. Is there oxygen present in air? Yes, there is. Is there water present in air? Yes, there is. Water vapour is present in air. So did rusting occur in test tube A? Yes, it did. The iron nail rusted in test tube A because there's oxygen present and water vapour in the air as well. In test tube B, we had dry air, so we added calcium chloride to remove the moisture. Is oxygen present in air? Yes, it is. Is water present in this case? No, it's not, because we had that drying agent to remove the water. And did rusting occur? No, it didn't. Test tube C then, we have water. Is there oxygen present in water? Yes, there's oxygen present in water. It's dissolved in the water. That's why marine life can survive. Is there water present? Of course there's water present in test tube C. Did rusting occur? Yes, significant rusting occurred in test tube C. Then test tube D, we had our boiled water and oil. Was there oxygen present? No, so we boiled the water to remove the oxygen and then put a layer of oil to stop oxygen dissolving back in. Was there water present? Yes, the iron nail is sitting in water. But did rusting occur? No. So what can we see from these results? So the only test tubes, the only iron nails that rusted were in test tube A and test tube C. Did that match up with your prediction? If not, that's okay. It's just important that you understand why rusting occurred in test tube A and C, but not in B and D. What can we see from our results? Well, if rusting only occurred in test tube A and C, those are the only test tubes that contained both water and oxygen. So when water and oxygen are present, rusting does occur. But if you look at test tube B, oxygen was present, but water was not present, and so rusting didn't occur. So oxygen by itself is not enough for rusting to occur. Now if we look at test tube D, oxygen wasn't present, water was, but we still had no rusting. So water by itself is not enough for rusting. We need oxygen and water present for rusting to occur. So that's what we're going to write in our conclusion. So in your conclusion, you don't have to write what I have written word for word, but you need to make very clear that the results of this experiment show that water and oxygen are both required for rusting. because rust is the product of the reaction between iron, water and oxygen. We're producing hydrated iron 3 oxide. There's no rusting in B because the anhydrous calcium chloride removes the water, and that means only oxygen is present, and so rusting doesn't occur because water is not present. And there's no rusting in D because boiling the water removes the oxygen, which means only water is present, not oxygen. And so therefore rusting doesn't occur either because we don't have oxygen present. So the results of this experiment show that we need both water and oxygen for rusting to occur. So if you were asked in an exam what conditions are needed for rusting to occur, you would say water and oxygen. You sometimes get a mark for saying moisture instead of water and air instead of oxygen, but you're much better at writing water and oxygen because those are the chemical reactants that iron react with in order to produce rust. We're now going to take some time to look at methods that are used to prevent rust. This is really key in industry because iron and steel are extensively used in construction. They're used to make structures for buildings, they're used to make bridges, among many other uses. So rust can be a major problem because it can cause bridges and structures that are made out of iron and steel to weaken. So if you've got rust being produced, remember we talked about that iron, hydrated iron oxide, the rust flaking away and exposing fresh iron, and over time that's just wearing away. And so will cause those structures to weaken. I've got a picture here of the effects that can have. So this is a picture of a bridge in Minnesota in America that back in 2007 this bridge collapsed, and you can see evidence of rusting on this bridge here and here, for example. You can see that these steel frames have started to rust, and that will cause the bridge to weaken. And in this case, we have a bridge collapse that caused the death of 13 people. So rust prevention is really important for protecting people's lives. It can be extremely dangerous if rust is allowed to get out of control. Rust can also cause damage to cars. It can cause problems, but it can also be what we call an eyesore. In other words, it's not pleasant to look at. But if you see here, you've got evidence of rusting on your car, and that can actually cause the steel frame of a car to wear away, and again that can be dangerous. So it's why it's important if a car has deep scratches to get that repaired, not just because scratches are not nice to look at on a car, but actually because if you leave the steel frame of the car exposed to the air, it will rust over time, and that can cause more damage. So it's really important that we prevent rust from occurring in the first place. So there's 3 broad categories of preventative methods that are used, and you can see this in our flow diagram as well. First of all, we've got barrier methods, and that does exactly what it says. It coats the iron or the steel in something. It can be various different things, which we'll look at in a second. But essentially that's providing a barrier between the iron and the air. So say you had an iron nail. Barrier methods is about coating the iron nail in something, in some other material that won't rust, and it's providing a barrier between the iron nail and the air. So you can see here from this diagram that the barrier is stopping the oxygen or the water from the air from getting to the iron. That barrier can be, as you can see from the flow diagram below, that can be something like paint, it could be oil or grease, it could be a plastic coating, or it could even be plating with another metal. We'll look at that in more detail in a second, but essentially barrier methods do exactly what they suggest. They provide a barrier between the iron and the oxygen and the water in the air or whatever environment they're in. The second method is something called sacrificial protection, and that's where we use a more reactive metal than iron to actually corrode or react with the oxygen or the water instead of the iron. So we're using a more reactive metal in that case. We'll come back to that again as well. And the third method is alloying, so mixing with another metal or another non-metal that will not rust. and so therefore lowering your chances of your mixture rusting. The iron within the mixture will still rust, but if it's mixed with other metals or non-metals that don't rust, then it will rust less. So let's look at each one of these briefly in turn. So first of all, let's look at barrier methods. And as we looked at on the previous page, these methods work by providing a barrier that prevents the surface of the iron from coming into contact with water and air or oxygen. And there's a number of methods that fall into this category, and sometimes in an exam you're asked to suggest which barrier method may be the most appropriate for a particular use. So for example, with cars that we're going to look at first, you're not going to use a coat of oil over your car to prevent rust. That would be a very time consuming process, a very strange process, and actually a very dangerous process if you've got oil on all your cars in the streets that will then run off onto the road and make the road surfaces very slippy. So you've got to think about, well, what method is appropriate for the particular use. So which of the 4 barrier methods do you think we would use for cars, bridges and railings? What barrier method do we use to prevent rusting? In this case we would use painting. So cars are painted, bridges are painted, railings are painted, and that layer of paint provides a barrier between the surface of the iron and the water and the air that it could come into contact with. What about tools and machineries? How do we prevent rusting in those uses? In this case, we would use oiling or greasing. So coating the tools and the machinery with oil will prevent the water and the oxygen in the air from getting to those tools, and therefore the iron within the tools will not react with water and oxygen. What about the likes of bicycle handlebars, garden chairs, a dish rack, so when you wash your dishes, what you put your dishes on when you're allowing them to dry, and cars, particularly bumpers of cars? In this case, your best method of prevention would be plastic coating. So coating these objects in plastic to prevent the water or oxygen from getting to the iron. And then lastly, we've got plating with another metal. Again, we can use here another metal to coat our iron in that will provide a barrier between the iron and the water and the air. Generally we use a less reactive metal, or a metal that is not prone to corrosion. So for example, tin is used in making cans for food. It's unreactive and it's non-toxic, so it's not going to affect your food that is in the can. We use chromium for vehicle bumpers and to coat steel, and even for bicycle handlebars to give it a shiny, attractive appearance. And we apply both of those by electrolysis. But if you use zinc, it has a special name called galvanizing. So if the metal that we use to plate our iron with is zinc, then we call it galvanizing. And zinc actually works in 2 ways. It's more reactive than iron, so actually it provides that barrier if the iron is fully coated by the zinc, but also if the surface is scratched, then galvanizing will also protect by sacrificial protection. We talked about that briefly in the previous page, and we're going to look at it on the next page as our next method of rust prevention. So if we coat our object in zinc, that's called galvanizing, and because zinc is more reactive than iron, if the surface is scratched, if the surface of the zinc is scratched, it can protect by sacrificial protection. And that's the idea, that because zinc is more reactive than iron, it will react with the water and oxygen first, which will protect the iron, but we'll have a closer look at that in a second. So here's your barrier methods. We've got painting, oiling, plastic coating and plating with another metal. Again, all of these methods of rust prevention will provide a barrier between your iron and the oxygen in the water to prevent it from reacting with it, which will prevent rust from forming. And as I say, sometimes in the exam you're asked to choose the most appropriate method for preventing rust. For some things like cars, you'll have multiple different methods of rust prevention that you could use, like painting and plastic coating, depending on what part of the car, or even plating with another metal, but you're trying to choose the most appropriate method. The next method of rust prevention that we're going to look at is sacrificial protection. So this is a totally different category of rust prevention. Sacrificial protection is the protection of iron or steel from rusting using a more reactive metal. This is really, really important. This is the one at higher tier that they would most commonly ask about. Essentially what you do is you attach a metal that is higher up in the reactivity series. What we mean by the reactivity series is a list of metals in order of their reactivity, with the most reactive metal at the top, the least reactive metal at the bottom. So essentially what you're doing is attaching a more reactive metal, and that will react with any oxygen or water present first. Do not say it reacts with the water or oxygen more quickly. That's not accepted in the exam. It reacts with the water or oxygen first, which prevents the iron from reacting. So in this sense, the other metal essentially sacrifices itself, reacting with the oxygen or water in the place of iron. And what you need to do then is, if that metal is going to react with the oxygen and the water, you need to keep an eye on it, because when it's almost corroded, you need to replace it, because otherwise, once that has all reacted with the iron, with the oxygen and the water, then the iron will then start to react. So that's the key idea of this more reactive metal reacting first. Once it has all reacted and worn away, then the iron will react. So you need to keep an eye on it and replace that more reactive metal when they are almost corroded. So you can see here on this side of a ship, you have some magnesium and zinc bars. Magnesium and zinc are the most commonly used metals in sacrificial protection, because you don't want a metal like sodium or potassium, which is going to react explosively with any water that it gets in contact with, and you don't want your object to then end up exploding because of it. So we use magnesium and zinc, which are more reactive than iron, but they still react fairly slowly with water. So if we attach them to the sides of ships, petrol storage tanks and underwater pipes, then they can prevent rusting. The magnesium or the zinc corrodes instead of the iron or the steel. So the magnesium and the zinc will react with oxygen and water first. So essentially you've got these magnesium or zinc bars on the side of iron or steel. So essentially all of it is exposed to the water and oxygen, but because magnesium and zinc are more reactive than iron, they will react with the oxygen and water first, but then once they've all worn away, once they have totally corroded, then the iron will start to react with the water and oxygen. So you've got to be careful to replace the magnesium and zinc bars before they fully react. So that idea of sacrificial protection is really important. You're attaching either magnesium or zinc because they are more reactive than iron, and they will react with the water and oxygen first. So don't say more quickly, say that they react with the water or oxygen first before the iron. We talked about this briefly on the previous page, that galvanizing is when you plate your iron or steel with zinc in particular, and it has a dual protection against rust. When the iron object is fully covered in zinc, it acts as a barrier. So that's our method 1, our barrier method. But when our object is only partially covered in zinc, or if the zinc coating becomes chipped or scratched, it acts as sacrificial protection. So even though the air and water are now in contact with the iron, perhaps below the zinc coating if it's been scratched, the water and oxygen will react with the zinc first because it is higher up in the reactivity series. Or in other words, zinc is more reactive than iron. So take some time, maybe pause the video, read through that information again, make sure that you can get your head around that idea, because this is asked quite often in an exam, and it's important that you get your language right, your explanations right, when you're providing those explanations in an exam, because the key terms that you use are really important with this. And then finally, we have our third method of rust prevention, and that is alloying, and this is much more brief. So you'll know from year 11 that an alloy is a mixture of two or more elements, at least one of which is a metal. So write that definition into your box. It's really important that you don't just say an alloy is a mixture of metals, because it can be a mixture of metals, but it can also be a mixture of a metal with a non-metal. So this is a method of rust prevention in that we would take our iron and we would mix it with another element. It could be another metal or it could be a non-metal. For example, steel is actually an alloy of iron and carbon. It is the element iron mixed with the element carbon. Alloys possess the properties of all of the elements that make it up. That's one of the properties of a mixture. We're not actually reacting these different metals together, or the metals and the non-metals. We're not reacting them together, we're just mixing them together. And so the alloy will possess the properties of all of the elements that make it up. So for example, if we wanted to use iron for a structure, because iron is very good, it is strong, and it is relatively cheap compared to other metals, so it is used widely in construction, but we know that it rusts very easily, so we may mix it with another element such as another metal or even carbon to produce steel. And that will make it less likely to rust. So we would tend to mix it with another metal or carbon that is not prone to rusting. So as a result, we have a mixture that contains iron, so it possesses the good properties of iron, but it is more resistant to corrosion or rusting because of the other elements that are present. So for example, stainless steel is an alloy that is resistant to corrosion, and we use it in things like saucepans, cutleries and hot water tanks. So quite a lot of your saucepans that you use to boil your potatoes or your carrots at home will be made out of stainless steel. And obviously they're resistant to corrosion, not completely. They do still have iron there, so they could rust, but because they're mixed with other metals or carbon, then they are less prone to corrosion. So you have your three different categories of rust prevention. You have barrier methods, sacrificial protection, and now alloying. And we've looked at all three in turn. It's really important that you learn each of them, how they work, and what particular uses those methods would be used on. And that brings us to the end of our section on rusting and rust prevention. What I'd like you to do now is to complete the questions on the next 2 pages of your booklet, so on page 23 and 24. There are 7 questions in total. Quite a few of them will just be short answers. So for example, there 1A, what is the chemical name of rust? You just need to write down the name. If you want to help yourself learn that, I would suggest writing the chemical name of rust is, and so on. So some of these are very short answers. Question 5, you just need to name the method of rust prevention. You don't need to go into too much detail. So this shouldn't take you too long at all. So complete these questions. Make sure you do questions 1 to 7. There's 2 more on the next page. Complete them in your blue book or on file paper. Use your notes. There should be nothing in these questions that you can't do. So use your notes to answer these carefully. Just be particularly careful, I would say, about explaining sacrificial protection. Be careful about the language that you use with that. So complete these questions now before you move on to the next video on the blast furnace.